Alright, I'm going to continue our work on the quadratics test review. Number 6, starting with identifying the A is -2, the B is -4, and the C is 2. I'm going to first start by calculating the axis of symmetry. X equals the opposite of B, so the opposite of -4, all over 2 times the A value, and the A here is -2. The opposite of -4 is 4. It's over -4, so I'm going to have -1 as my X value of the vertex and my axis of symmetry. The vertical line equation of the X for the axis of symmetry is X equals 1. The vertex is going to sit at, oh, I'm sorry, it was -1. The vertex is going to sit at -1, and we'll use the equation when X is -1 to find the Y value. And I grabbed a calculator so I can move on with help of my calculator. So the first thing that I'm going to do is just -2, right, parentheses around my -1. Take it to the second power, -4 times -1 plus 2. So the Y value of my vertex is 4. The vertex for this equation is -1 and 4. Axis of symmetry, X equals -1. This is going to open down because of the -2. I had looked at the tables for 7, 8, 9, and 10, and I'm assuming you have already as well. I identified number 7 as a linear relationship because it was adding 5 all the way through the Y values. As X went up by 1, these all went up by 1, up by 1. As X went up by 1, we added 5. The B, okay, so my slope is going to be 5, the change. The B value, or the starting value, is when X is 0, so my B is 1. I have to find the equation for the table. I'm going to write it this way. Y equals 5X plus 1. For number 8, I noticed that this relationship is actually doubling. It's multiplied by 2 as X is going up by 1. Every value has been multiplied by 2. Every value is 2 times its previous. This is actually an exponential. I'm going to put that in parentheses. But the question is it linear, quadratic, or neither? So in this case, I'm just going to say it's neither. That doubling idea comes from an exponential relationship. When I looked at number 9 and number 10, in number 9, I noticed that we had, as X was increasing, I was seeing the pattern, this symmetric pattern in the table, as we do for a quadratic. And so in order to write the equation for this quadratic, I'm going to have to give myself some paper to work on. Use one of the points, X and Y. And I don't know which one you chose, but I'm going to use -3 and 1. No, I'm not. I'm going to use +3 and 1. If I have a choice about what points I'm going to use, I'd like to pick ones that are positive. Regardless of what point you use, we should still wind up with the same A value. My intent right now is to use the H and the K, the vertex, 0, -2, and write a quadratic equation for this relationship in the form of Y equals A times X minus H, all to the second power plus K. My H and K are 0 and -2. I'll put those in after I calculate and find my A value. So what I'm going to do is solve and plug in Y equals my missing A times the quantity 3 minus 0, X minus H squared plus K. In this case, my K is negative, so I'm going to write it as minus 2. A times 3 squared minus 2. 1 equals 9A. I got my 9 from taking 3 to the second power. Minus 2, if I add 2 to both sides, I'm going to find out that 3 equals 9A. Divide both sides by 9. My A value is 1/3. This is going to be a fat parabola. Oops, sorry about that. That 1/3 A is going to make the parabola wider than 1x squared. So to finish, I'm going to use my vertex H and K and the 1/3 I found for A and write it as Y equals 1/3 times the quantity X minus 0 squared, my H value, plus K. In this case, it's -2. I'm actually going to rewrite this in a simpler form. 1/3 times X squared. X minus 0 is just X minus 2. That would be the best answer in that case. And I also found when I go on to number 10, I